If you start with a basis that's too large, for example, if we're looking at a basis of P2, polynomials with degree at most 2, the dimension of P2 is 3, which means all the bases of P2 have to have 3 vectors in them. As we can see in the vector space V, it's spanning. It reaches the whole space, but there's 4 vectors, so that means there is linear dependence. Here we can see we can delete 2v1 because that's redundant, and the remaining 3 vectors would then be independent and still span the space, thus forming a basis. On the other hand, if we started with a set like U, if we say v1 and v2 are independent, that's not enough. We need 3 vectors in order to span the whole space. So we would have to add on a 3rd vector that's also linearly independent in order to form a basis. In order to enlarge a set to form a basis, we need to be familiar with the independent and dependent lemma. Let's say that S is an independent set in V. If we add in a new vector, let's say U, and U is not in the span of these VI's, this is true if and only if the set S plus U, vector U, this is only true if this new set is independent. This would be useful if we're enlarging a set that's already independent to form a basis. If we add in a new vector and it's not in the span of the existing vectors in the set, then this vector is also independent. On the other hand, if we keep adding new vectors and then we reach a point where U is included in the span of these VI's, this means that the set S plus vector U is dependent. If U is in the span of the V's, that would mean we could write it as U equals A1 V1 plus all the way till AN Vn. U is just a linear combination of the existing vectors. If this is true, if we move the U to the opposite side, we get the 0 vector is equal to negative U plus A1 V1 till AN Vn. So we can generate the 0 vector without having all the coefficients equal to 0, so we see that this set is dependent. Now that definitions are out of the way, let's try an example. Carve a basis from this set of vectors for V, where V is R3, so all coordinates x, y, z. We know that this is 3-dimensional, so we know we're looking for 3 of these 5 vectors. First of all, we can cross out the 0 vector right away because the 0 vector doesn't add anything. In fact, any set with the 0 vector is always dependent because you can write it as a linear combination of all the other vectors with a 0 coefficient. To find if the remaining vectors are independent, we can write them as a linear combination equal to the 0 vector. Next, we can simplify the left side. We see that our 3 equations are going to be the first term equals 0, the second term equals 0, and our third term equals 0. So we can put this in a matrix to solve it. This is a homogeneous system, meaning that the constant column has all zeros, so we don't really need to write that portion. We have A in the first column, B in the second, C, and then D. We could have equally gone straight from here to the matrix by writing each vector as a column. Now that we have our coefficient matrix, we can reduce. So let's do row 2 minus row 1. We're trying to get zeros under the leading one. Row 3 plus row 1, we get 0, 0 minus 2, 1 minus negative 1, and 2 minus 1. On the bottom, we get 1 plus 2, negative 2 plus negative 1, and 1 plus 1. Next, we want a leading one here. If we divide by negative 2, we'll get fractions, so to avoid that, let's do row 2 plus row 3. Next, we want zeros above and below the leading one. Row 1 minus 2 row 2. Row 3 minus 3 row 2. Negative 1 plus 2, 1 minus 6. On the bottom we have 0, 0, negative 3 plus 3 is 0, 2 minus 9. Now we want a leading one down here, so let's do row 3 divided by negative 7. And lastly, to get zeros above the leading one, we'll do row 1 plus 5 row 3, row 2 minus 3 row 3. Now we have our matrix in reduced row echelon form. Since not all the columns have a leading one, the third column is dependent on the other columns. In fact, we could really eliminate any of these 4 vectors because they're all dependent. If we eliminate one, we're going to get an independent set. But in this case, it's clear that the third vector is just a linear combination of 1 times the first vector minus the second vector. Let's double check this is true. 1 minus 2 minus 1, 1, and -1 minus 1 is -2. And if we eliminate its column, the remaining 3 vectors are independent. 3 is the dimension of R3, therefore these 3 remaining vectors must form a basis. Next, let's try to generate a matrix of M22, the set of all 2 by 2 matrix, from this set. First of all, how many matrices do we need? The dimension of M22 is 4, 2 times 2. So we're looking for 4 independent matrices to form a basis. First of all, let's check that these 3 matrices are independent. Then we can proceed with adding a matrix. Since there's more than 2, we can't just look at them and say, oh, they're not multiples of one another, so they're independent. Here we have to actually check. Our 3 equations are going to be A equals 0, B equals 0, B equals 0 again, and A plus C equals 0. So we clearly get C equals 0. Because there's the trivial solution only, the existing set, let's call this set S, is independent. One strategy would be to guess matrices, but if you had more difficult numbers, it might not be feasible to do that. So let's try a systematic approach. From the independent lemma, let's call this X, Y, and Z. If we added a new matrix, let's say U, X, Y, and Z are independent if and only if our new matrix, U, is not in the span of the first 3 matrices. What does this mean again? U is not a linear combination of X, Y, and Z. Let's set up an arbitrary U, U1, U2, U3, and U4 equals, well, we already know what the linear combination of AX plus BY plus CZ is, so we'll write that out. What equations do we get? U1 equals A, U2 equals B, U3 equals B, and U4 equals A plus C. Next, we need to pick values for U1 through to U4 so that one of these equations or multiple of these equations are not satisfied. Let's make this as simple as possible. Let's set U1 equal to 0. And what does this mean? This means A equals 0. Let's say U2 equals 0. This means that B equals 0. And let's set U4 equal to 0. This means that C equals 0. And we can't have all zeros because that would be dependent. In order to make this not work, let's say that U3 is not 0. In this case, there's no possible A, B, and C that will generate U, our new matrix. Let's now plug in our values. U1 is 0, U2 is 0, U4 is 0, U3 is not 0, so let's just say 1. This new matrix is not in the span of X, Y, and Z. Therefore, our new set with 4 matrices is independent, and because the dimension of M22 is 4, it forms a basis.